It's a distinct pleasure to be able to introduce this evening's speaker, Dr. Joseph Liu from the Honeywell Corporation. Dr. Liu got his undergraduate degree from Zhejiang University in China, his master's degree from the Beijing Institute of Technology, also in China, both degrees in chemical engineering, and he got his PhD in chemical engineering from the University of Washington. After his graduate studies, Joseph went on to work at Honeywell, where he's been involved in a number of process control applications. He's the lead inventor for their unit-wide control application, as well as their multi-unit process control application. He's an inventor on over 20 patents with Honeywell. He holds the title of Chief Scientist for Advanced Control at Honeywell and is a senior fellow at Honeywell. In 2010, he was recognized with the Control Engineering Practice Award from the American Automatic Control Council, and he is a member of the IEEE. So without further ado, I'm going to invite Joseph up to the podium to give us a lecture on bridging the gap between planning and control, a cascaded MPC approach.
Thank you, Frank. Good evening, everyone. Thank you, Professor Doyle, for your kind introduction. I would like also thank Professor Craig and the organizing committee for inviting me. It is indeed an honor and a privilege for me to speak here. In the next hour or so, I would like to share with you the Honeywell's perspective on bridging the gap between planning and control, and some of the work that we've done in this area. First, I would like to provide some background. Process industry have made a lot of progress in the last 30 years in terms of real-time control and optimization. Close to 10,000 MPC applications have been implemented in different process industries. Oil refining, petrochemical, pulp and paper, aluminum, oil and gas, just to name a few. In terms of plan-wide optimization, a little over 100 plan-wide optimizers have been implemented in various areas, well, mostly in the ethylene plants. The total estimated benefits have reached more than $10 billion for all the process industry, $5 billion of which was delivered by Honeywell since 1996. All the success stories aside, to further broaden the reach of control and to deliver more benefits for our customers, several improvement opportunities exist. First is solution scalability. Not all the solutions we have right now can be easily scaled up. For instance, the ethylene-wide, plan-wide optimization, the implementation we did, the first one we did, was about 20 years ago. And since then, we have not been able to scale up the solution for a larger scope of the plan or more complex plan. So it seems like we have hit a glass ceiling of upward mobility in terms of solution scope. The second area is operability. By operability, I mean the certain required flexibility of the solution. So some of the solutions are too monolithic. They're either or on or off. They can't deal with the issues such as unit shutdown, instrumentation maintenance, or the unit upset. Those are the local area issues. The third area is the real-time responsiveness. For example, steady state RTO would require the process to reach the steady state before it can optimize. When the disturbance comes in, it has to wait. So it misses the opportunity to reject the disturbance right away. The proposed multi-scale MPC cascade solution is aimed to further broaden the reach of control to solve a new kind of class of problem. And more specifically in this presentation, to bridge the gap between planning and control. Everyone here is familiar with PID cascade. So the MPC cascade can be similarly constructed. If we compare the two, there are two important differences. First, there are multiple slave loops. So in other words, we can have multiple slave MPCs. Each controls a process unit. When all the process units inside the plant are controlled by slave MPC, then the master MPC can control an entire plant. That's the design idea anyway. The second difference is that both master and slave controller have an embedded optimizer. Here's a small box. You may not be able to read the text here. So in other words, the slave MPC can optimize in a unit, and the master controller can optimize the entire plant. If we leave the process dynamics out for the moment, just focus on the control structure, then the MPC cascade can be described by this diagram where one master MPC cascade on top of multiple slave MPCs. For some of the plants that we have looked at, this number n here can be pretty big, somewhere between 15 to 80 if we want to control the entire process plant. Both master MPC and the slave MPC can employ a dynamic model. For some applications, the master MPC can employ a model at the coarse scale, whereas the slave MPC can employ a model at the finer scale. This means that the modeling scale between the master and the slave don't have to be the same. If we place a more familiar automation system hierarchy next to the MPC cascade, then it appears to be clear then this row of slave MPCs would fit in layer 2. It is not as clear where the master would fit exactly. However, it is probably safe to say that the master MPC should be solving the kind of problem that are currently addressed by the tools in layer 3, such as planning. Okay. What kind of interesting problem that the cascade MPC can solve? One such interesting problem is just-in-time manufacturing. Here I will use oil refinery as an example to illustrate. This is the picture of oil refinery, which contains many process units. From the modeling perspective, an oil refinery or a process plant can be modeled by a flow sheet diagram such as this one. So in a flow sheet modeling, a process unit is modeled as a box. A process unit box contains typically one input, which represents the feed, and multiple outputs, which represents the product streams from that process unit. Then different process boxes can be connected in a network, such as this one, to represent realistically the configurations inside the plant. So the just-in-time manufacturing problem then can be described as for the product deliveries that we know in the near future, produce just enough components inside the plant at a quality that is just enough to meet the product quality requirements at the end. So in general, this is a steady-state optimization problem. For some applications, however, we need a dynamic version of that. Typically when we need to control the inventories tightly within the plant. So when you include the inventory locations where you need to control the inventory, making sure none of the inventory levels exceeding its high limit at any given time or going below its low limit at any given time, then this problem becomes a dynamic one. Of course, we need modeled process unit box dynamically as well, which means that each process box here would contain a set of dynamic models. To make my description a little bit easier, I'd like to divide this refinery into two halves. The pink region represents the distillate production portion of the refinery, or colloquially we call it diesel pool. The product of that pool includes jet fuel, diesel, heating oils, and some furnace oils. This scope is easier, contains fewer number of processes. However, we don't lose generality by reduce the scope, because all the important plant-wide control problems still are represented in this scope. In other words, whatever the solution we can come up with for this diesel pool, it is probably reasonable to say that it can be extended into the entire refinery. So we're going to leave the other half out for now, which is the gasoline production, and just focus on the distillate pool for now. Here's an example of a diesel pool in which we have 3 crew units and 2 vacuum towers, and then 3 hydrotreating units that makes the distillate components. The components are then stored in one of those component tanks, and of course the switches can be made, if this one's full, you can switch into the other tank. The final product is made from mixing the components from one of those 3 tanks, or sometimes you can combine 3, or sometimes you can choose 2 out of the 3. The vector length here represents the product delivery amount, and of course those delivery amount changes day by day. So the pink lines here represent the routing decision variables that we have to establish the material balance inside plant, also for meeting the product delivery on the right side. So this seems to be a fairly well-posed inventory control problem. Now, of course, right now we're modeling this diesel pool at the coarse scale. So each process unit contains a lot of details. For instance, if we drill down at this hydrocracker here, of course, a unit is actually a very complex chemical process equipment, or working together to achieve a certain production goals. Let's enlarge it further so we can see it better. So if for some reason, let's say for the purpose of establish better material balance, we need increase the feed to the hydrocracker, then feed has to go through multiple steps here, and finally it will be separate into different components at the end. So at the high level, we could assume that each one of those processing steps could become a bottleneck for the feed increase that's requested either by a person or by a controller. The unit level multivariable control is very well suited for this kind of problem. So it will know how to utilize the resources available within the process unit in order to process the feed change requested by either person or something else, and still satisfy the product quality requirements. So that's where actually 10,000 MPC controller have gone into. Okay, so we know how to define this problem, how to solve this problem very well. And for formulating the plant-wide control problem in this distillate pool, we want to keep this guy encapsulated, right? Otherwise, we may not be able to see the forest for the trees. So as long as the unit level multivariable control can process the feed request by either the master or by the person, then this inventory control problem is fairly well posted. In addition to inventory control, there's also other parts of the plant-wide control problem that need to be taken care of. One such aspect is quality control. The first example of quality control in the diesel pool is sulfur control. Sulfur is a form of impurity that originally comes from the feed. Within the diesel pool, those are the 3 blue units that can remove sulfur from its feed. Of course, each comes at a different cost structure. So if we look at the product sulfur requirement on the right side, it typically around 10 to 12 ppm. So it may appears to be a unit-wide control problem. We just need to set sulfur targets on one of every 3 units. We say, well, let's say put it at 10 ppm. Well, it turns out that the problem is not that simple, because the cost structure of those blue units are very different. Some units can remove sulfur at a much lower cost, since the final product is mixed from the components, so the low-cost unit can over-remove sulfur, and the higher-cost unit can under-remove sulfur. And at the end, we still be able to meet the product requirement, the property requirement, right? So this now becomes a plant-wide control problem. You can't just make any unit specify certain things in a unit to achieve this goal. So the goal of the sulfur control then is to remove just enough sulfur at the lowest processing cost overall. The second example is cloud point. Cloud point is the temperature at which the final product will start to freeze. If we want our cars to start in the winter, or better yet, if we want our airplane engine not to stall in the midair, this is a very important quality to control. Within the diesel pool, those 5 blue units have the control handles to reduce the cloud point. And the picture here is very similar to the sulfur control, is the plant-wide control problem. You cannot get any individual unit to achieve the overall task. There are actually 6 more parameters or quality parameters we need to control in the diesel pool. The essence of those other quality control is very similar to the 2 that I just shared with you here. So in the interest of time, I'm not going to go through them. Combining the quality control and inventory balance, this forms a very interesting multivariable dynamic control problem, right? At this point, unfortunately, there is no closed-loop tool available to control this problem. The closest solution we can find is an open-loop planning solution that solves the steady-state version of this problem. The planning solution is executed typically once a week, and if somebody wants to execute more frequently, maybe once every several days. So typically, a person then is brought into loop. He would start from the results of planning solution and then make daily adjustment based on his heuristics. So typically then he would look at the inventory positions inside the refinery and look at the delivery requirements. Then he would heuristically make adjustments on unit feed rates and the quality specifications of each individual unit. And that person typically does not work in the weekend or holidays. So in other words, we get 5 control moves a week. That's the current situation. The MPC cascade that we proposed here is certainly very suitable for solving this kind of problem, right? So to do so, first we need to build a dynamic matrix for the master MPC, because the slave MPC is already there. The output of this dynamic matrix contains controlled variables, or CVs for short. The CVs can be any quality-related parameters or production-related variables that we want to control. For instance, In this specific example, I put in the component tank levels or the component tank quality parameters such as the sulfur and the cloud point. The input to this model matrix contains manipulated variables, or MVs for short. The MVs are typically the feed rates to the crew units or the quality control handles that we just discussed. The last column is the disturbance variable. A good example of disturbance variable is product delivery. Those are the things we know, but we cannot manipulate it directly. Now, surprisingly enough, for the several examples that we have looked at, this model matrix, the dynamics is very simple. Typically, each individual submodels, we can use just the second order or first order with integrator. That's sufficient enough to describe the dynamics. Notice that there's no set point in this control problem. The reason is that, one, those component tanks are huge. It takes about 5 to 15 days to fill up. So the process dynamics, however, is relatively fast compared to the component tank. It typically, the time constant of process unit typically is somewhere between 1 hour to several hours, usually less than 3. So it makes no practical sense to put a set point on any one of those controlled variables. The second reason is that in process industry, typically the number of CV is about twice as many as the number of inputs you have. So if you put all the set points here, you're going to overspecify the problem. So it is very important for the master MPC at least to provide constraint control. At Honeywell, we have been using a form of model predictive range control that provides both regulatory control and constraint control in a unified formulation in the last 20 years. Here, in the interest of time, I can only give you a high-level summary. Let's start out from the least square version of MPC formulation that most of you are familiar with. In this formulation, we minimize the future air. The air is weighted by Q matrix, then with additional input move penalty term. A is the step response model, delta U is future input move, Y hat is the output prediction, R is the internal reference trajectory. If we replace R with the slack variable S, then effectively in this formulation we replace the parabolic penalty function with a bathtub-shaped one. So in other words, in this formulation here now, we are providing double-sided constraint control in general. Hence, the name range control. If there are degrees freedom left, then we can add additional optimization term to this range control formulation. In this specific case, the optimization term just include the minimization of output Y. In other words, we're just tilting the bottom of the bathtub a little bit towards left. And we will be pushing the output towards the lower bound when there are degrees of freedom left. Now, the control performance then is specified by correction horizon here, which is shorter than prediction horizon. And adjustable funnels can be used to specify dynamic constraints of this problem. The funnel end can be either open, as shown in the top graph, or closed, as shown in the bottom graph. So in the top graph, when funnel end is open, we provide range control, or double-sided constraint control. In the bottom graph, when the funnel end is closed, we provide regulatory control. In either case, there are generally infinite number of solutions to this control problem because the funnel beginning portion is always open. So analytically, we need a two-stage approach to solve this problem. In the first stage, we solved the range control problem just like normally we would. And then if the solution to this problem is not unique, then we need to add a secondary optimization to help us narrow down the choice of control solution. And typically, we would use a weighted two-norm. The weights are chosen just in case the input engineering units are not properly selected. On line algorithm, however, we can combine these two stages together. In the process of searching for the solution of range control problem, we can keep track of active rows and columns of A matrix. And then the active set of A matrix then can be properly weighted by certain weights that we choose. Then it can be then further decomposed into URV decompositions, where U and V are unitary, R is triangular. Now, URV decomposition is a lot proficient or less expensive CPU-wise than SVD decomposition, particularly in terms of rank 1 updating, which is what's required in solving this problem in the iterations. So typically when we test it, it's about more than 10 times faster. That's why we choose the URV decomposition. URV decomposition also contains a very important SVD feature that we need. When the final solution is not unique, URV decomposition will render a two-norm minimum solution. Since the A matrix is properly weighted, then we would get a weighted two-norm minimum solution, which is what we want. So this is how we actually solve the range control MPC problem. Now, if we install the MPC range control in both master and the slave, can we then solve the just-in-time manufacturing problem in closed loop? The answer is yes, if the solution from the master is always implementable by slaves. The answer is no. If the master solution will cause one or more slave MPC to wind up. By wind up, I mean the master solution will cause sustained constraint violations in slave controller at the steady state. If there's a dynamic violation, we can always do some tricks in the slave to handle it. But if it's a sustained steady state violation, the slaves just cannot handle it at all. So the real challenge then is, how do we get the master to understand enough about slave constraints so that it would not generate a solution that would cause wind up? Or better yet, it would always generate the solution that would respect the constraints inside the slave. Notice that we don't have to include all the slave constraints into the master. Some of the slave constraints has nothing to do with this plan-wide optimization problem. So it's not a good idea to append all the slave constraints into the master. So we need to look for a better way to represent slave constraints in the master so that the master can respect the constraints inside the slave. In order to analyze this problem one step further, we need to put the master models side by side with the slave models. In this diagram, the top portion is the master MPC model, which is partitioned into different column groups. The lower half are the slave models that are block diagonally arranged. Notice that an MV of master may also be an MV of slave. The reason is very simple. Let's use the hydrocracker feed as an example. The hydrocracker feed, let's say, is the MV3 of the master. Okay? So master wants to use it in order to do the property control and plan-wide inventory balances. The slave also wants to use it to do the local, to achieve the local objective. So whenever you have that situation, those variables are defined as conjoined MVs. Whenever you have a one conjoined MV, you lose a degree of freedom in the overall system, right? Now both sides will have to agree on the single value for that MV. So those conjoined MVs are the ones that conjoin the master and the slave together, like conjoined twins, if you will. The non-conjoined MVs are defined as free MVs. So now, how much the feed rate that master can use, namely the MV3, depends on the slave conditions, depends on the constraint conditions inside the slave MPC2. So for example, if some of the CVs in the MPC2 are not constrained and some of the free MVs are not constrained, it is possible to move the free MVs in such a direction to make more room for the master to use MV3. So the conjoined nature of this between the master and the slave makes the analysis of this problem a little bit more difficult. So to solve the problem step by step, let's look at the simplest case where we have only one conjoined variable per slave MPC. In other words, let's assume MV2 and MV4 inside master. They don't exist for now. We won't bring them back later, okay? For the simplest case, then we can solve this problem by the procedures we listed here. You might want to call it algorithm if you so choose. I will explain step by step by using this flow sheet of the refinery model. The hydrocracker, the example that we had, is right here. The feed to hydrocracker is MV3. Let's say the current value is 33, or whatever the value may be. Let's just, for example, just 33. Since inside the master, the hydrocracker is modeled at the course level. So the model inside the master for the hydrocracker is just one input and let's say 5 outputs, okay? It could be more. And we just have a very simple one-column dynamic model. However, the same hydrocracker is modeled at the finer scale by the slave controller. So the slave, inside the slave MPC model, there are a lot more number of CVs and MVs. Typically, they're about 40 by 20. Due to the space limitation here, I'm just showing you a very small subset of the slave models here, okay? Of course, the first MV is also the feed to the unit, which corresponds to the MV3 in the master. Its current value is also at the 33. The rest of the green values represent the current operating value for the rest of MVs and the CVs. Now, the master can make an inquiry call to the slave to maximize its feed. When that inquiry call is made, the results are displayed here. It will return a bunch of values. The maximum feed rate would be 38 and all the other corresponding values. The underlined values are here represents the corresponding variables actually active on their constraints. So in other words, if the feed rate actually is brought up to 38, then multiple CV MVs will be active on their constraints. Then the maximum value of 38 can be sent upward to the master and then used as high limit for its MV3. So in other words, if I conduct the MPC form algorithm here, just like regular MPC, but I include the proxy limit here, 38 as its high limit, then I will never generate a solution that would be higher than 38. In other words, the maximum feed rate of 38 becomes a proxy limit for all the constraints inside the slave. The master doesn't have to know anything more than that, just the one single proxy limit. The rest of slave constraints, it doesn't have to know. In general, the master may also need to know the low limit. So another inquiry call can be made to minimize the feed rate. Then the minimum value of feed rate can be sent up to the master and used as low limit for the MV3 of the master controller. When the master performs that same procedure for all the slave MPCs, then the master now knows everything it needs to know about slave constraints in order to generate the solutions that would respect constraints inside slave. So this is how we solve the simplest case where there is one conjoined MV variable. Okay, what if we have two or more conjoined MVs per slave? Well, more inquiry calls can be made to approximate the feasible region that's defined by slave constraints. Here's how it works. The horizontal axis represents the master conjoined MV number K. And the vertical is a conjoined MV number K plus 1 in general. These two conjoined master MVs corresponding to MV1 and MV2 inside the slave MPCI. So the high-low limits of the MPC1, MV1 and MV2 will be transferred over directly to the master's MV space because those are the two same variables anyway. The CV constraints inside the slave can also be plotted, excuse me, can also be plotted in the master MV space. The slopes of those CV constraints are determined by the first two columns of models inside the slave. The y-intercept of those slave constraints are determined by free MV values. So if the free MV values are not determined yet, then those constraints will move up and down a little bit, depends on the choice of free MV, right? So in general, the feasible region defined by slave constraint then can be sort of described by this beige area. Although we know the edge of that beige area can move in and out, depends on the choice of free MVs, okay? And this region is always convex, although the edge is not quite fixed yet, or some of the edges. Now, we can make an inquiry call, first inquiry call to maximize the case conjoint variable, to push the constraints all the way towards right? Mathematically, this inquiry call can be expressed as maximize the first conjoined variable subject to all the CVMV constraints inside the slave and with the choice of all the variables, the input variables in the slave. That includes, X includes both conjoined MV and free MV. We also need an additional equality constraints to specify the direction, which direction we're pushing the constraints out. So in the first call, D transpose is 0 and 1. That means the second conjoined MV is locked at 0. The first conjoined MVs can move freely, so which means we're pushing the constraints all the way towards right. So then we can make a second inquiry call to push the constraints all the way towards left. In that case, the objective functions will be, we will change the sign of objective function, but we will keep the equality constraints or directional vector unchanged. And then we can make a third inquiry call to push the constraints all the way up, and a fourth to push the constraints all the way down, and so on and so forth. In theory, we can make as many inquiry calls we want. But for this example, we will stop at 8. We feel it's good enough. All right. So if we connect the endpoints of those inquiry calls, then this enclosed area becomes the approximation of the feasible region that's defined by slave constraints. So if we carry those edge line forward into a master model and append it as additional proxy CV constraints here, and along with the proxy MV constraints that we talked about before, now master knows enough about slave's constraints that it will generate the solution that always respect the slave constraints. This is how we actually solve the master and slave cascade. And now the master and the slave can run just like a regular MPC dynamically. And the master will never have to worry about, well, would I actually generate the solution that the slave would not be able to implement? Okay, so I will show you some simulation results. A Honeywell customer requested us to perform actually they contracted us to perform a simulation study and to estimate the benefits of this potential solution. They provide a planning model and the plan economics, those, the cost structures that I just talked about, how you remove software, how you reduce the cloud point, and operating data were provided, okay? The study scope is exactly the distillation pool that I talked about, so I don't have to repeat the study scope. They also asked us to validate if the solution is the operability of the solution is good enough to handle, let's say, shutdowns of the units. So within the study period, 1 year, there are 3 instances of unit shutdown. The shortest one is 5 days of 1 unit. The longest one is 35 days. So you really have to sort of you have to cope with the situation. You have to sort of do your best when your unit is down. Of course, your slave MPC is down. The study scope will now include 1 more unit, which is the fluidized catalyst cracking unit, or FCC unit. The reason we include this unit is because this unit is the gateway to the other half of the refinery. So when we're doing the diesel pool optimization, we want to make sure that we keep the other half of the refinery constant or unchanged. That's why we include the FCC unit. All right, so this is a more detailed flow sheet diagram for the diesel pool. It includes more routing decision variables, as you would imagine. We included more inventory tanks that we need to control. And also the customer provide some additional information about the 3 reactive units. Those are the volumetric gains. Let's say the volumetric gain of 4% of this hydrotreater, it means that the combined product gains 4% in volume from its feed. The other way of explaining the volumetric gain is that average density of the product is reduced by 4%. Hence, the volume is going to increase. So the hydrocracker here has the highest volumetric gain because it breaks down the large molecules into smaller ones to produce the diesel component, and the average density is reduced by 20%, hence volumetric gain of 20%. Now, notice that in fuel industry, all the inventories are expressed in volume. Price is also expressed in volume. So whenever you have volumetric gain, you're like printing money, right? So the master knows how to leverage that. We will see in the simulation. Before we perform the closed loop simulation, we want to examine how well the current open loop planning solution is working, right? How well it's doing for the refinery. One way of examining the current performance is by taking a look at a very small scope, as shown here. We just focus on the components that were made during the study year. If the components can be mixed differently to produce a different mix of the product, which will help us to get more product value in the end, then we say the components were overqualified. If the components cannot be mixed to fetch more product value, then we say the components were optimally produced. In other words, the open loop planning solution is working well for the refinery. It turns out every month in the study year, the components can be mixed differently to fetching a lot more product value. So for instance, month number 5 here, the components were mostly used to produce product C. The same components can be mixed to make more product D, which is at the higher price point. So in other words, we're giving away some quality value because product D is at the higher quality grade. So the total product value difference between what was actually made and what could have been potentially made and sold is defined as quality giveaway in the industry. So, or quality overqualification. So the total quality giveaway in the study year is actually $65 million a year, or about $3 per barrel of product. Now, nowadays, the refining margin is very low. In general, typically, the refinery operating profit margin is somewhere, for diesel pool, is somewhere between $2 to $3. This means that if we could have produced the components more optimally, then we could have doubled profit. Okay, so in order to capture some of those benefits, we test out to put a master MPC to cover the entire diesel pool scope. And in the master MPC's optimizer, we include 2 terms. First term is the reduction of the component production cost, because we know there's $65 million left on the table, right? The second term is to minimize the feed cost. We want to ask the master MPC to further exploit the volumetric gains that's left the table by the planning solution. Of course, the planning solution is exploring it, but it's exploring the open loop. So let's see if there's additional room we can further exploit. Okay. So the master model actually was fairly easily constructed. The gains were extracted from the planning model. The dynamics then is further fleshed out from the operating data. The slave controllers are already in existence. There's nothing we need to do. So we just pull the slave controller offline and put the master MPCs on top of them, running the whole year simulation based on exactly the historical conditions for the slave controllers. So essentially, we relived the study year now with the master MPC in closed loop control. Okay, to do that, first we need to estimate proxy limit. So this is an example of one of the proxy limits that we estimate. There are a total of 28 of them, so I'm not going to show them all. This is the hydrocracker conversion rate. The blue line here is the historical value of the hydrocracker conversion rate. The green line here is the uppermost edge of that polygon, okay? And then, as you can see, throughout the year, it's a very volatile sort of picture, right? There's no good way of saying, well, you can move up by 5 or 10 or whatever. The second example I want to show you is another conjoined MV where the proxy limit calculation tells us there's not much room you can move. That doesn't mean that, you know, if you have a conjoined MV, that means you can use that a lot. For some cases, you may not. Like in this case, there's only about 1%. So it's almost useless, but that's okay. The master MPC can deal with the dynamic constraints, no problem. You know, whenever you set different constraints, it will cope with it, right? Okay. So with all the proxy limits estimated, then we can run the closed loop simulation for the whole study year. Notice that this is a plan-wide optimization problem. There's no set point. So don't look for a performance, so, oh yeah, this is going to reach a set point. No. Instead, you should be thinking in terms of which direction I should be pushing this output towards in order to make more profit for the refinery. Okay, so here's some examples in the component tank, 3. The cloud, I can't read. Okay, the first one is cloud point. Yes, cloud point. The resolution is really low. I'm sorry. The cloud point is being pushed higher most of the time throughout the year. The cloud point after master being put on is the blue curve. The stars are the historical performance of that tank, which receives the components from multiple units, okay? When the cloud point is being pushed higher, this means that low-cost, heavier component is being mixed into that tank in order to lower the average cost of that component inside tank. Same thing with the flash point. Flash point is reduced mostly throughout the year. That means the low-cost, lighter component is also being mixed into the tank in order to further reduce the average cost of the component inside the tank. And same thing with the 90%. 90% is also pushed high, so the average cost of the component is further reduced. Sulfur content is largely being controlled at high limit, 10 ppm, except there's a blip here where one of the units was shut down. That introduced the disturbance to the system. The other 2 unit shutdowns is not visible in sulfur, but it's visible in other components, okay? Now, the sulfur is a lot higher than the historical performance. That means in the study year, the refinery was removing sulfur, over-treating the sulfur. Of course, at a lot of cost of catalyst and the utility. The sulfur cost is very nonlinear. The last few ppms is very, very difficult to remove than the first initial 100 ppms. So, because it's impurity, right? So the total sulfur removal cost was significantly reduced. If we add all those four components together, then the total combined production cost for the components are significantly reduced. All right. Now, the master MPC also exploit volumetric gains beyond what the planning tool could exploit. So what the master controller knows is that since the hydrocracker has the highest volumetric gain, so master controller knows it needs to increase the conversion rate on that unit. When the conversion rate is increased, we can produce more diesel components while reducing the feed charge rate. We can produce the same amount of diesel components by lowering down the feed. So in other words, then further we can save feed here, okay? And when we increase the conversion rate, it introduced two companion changes. One, the component quality is lowered, because now you're mixing a lot of lighter component and heavier component into the distant components. So then the master controller knows how to compensate that by changing the quality factors on the handles on the two hydrotreating units. So overall, the components inside the tank still would be able to satisfy the final product delivery. Second companion change in the hydrocracker is that because now we're sending more materials to the diesel tank, right? So of course we're sending less component to the gasoline pool. The master knows how to compensate that by sending more gas oils from the crew unit. So overall, the other half of the refinery is kept constant. So combining all those effects together, we reduced the feed consumption by 0.5% and still be able to meet the product delivery requirement. In other words, we didn't reduce the diesel production. My customer would not let me to show you the actually feed rate change because that would disclose their production rates. But I can show you the relative feed change of 3 crew units here. And those delta changes are being laid on top of each other, so this is a very busy plot. If I fade out the individual delta feed changes of 3 crew units and just leave behind the combined delta feed change, as you can see here, on average, we reduce the total feed consumption by 0.5%. Okay, to conclude. A multi-scale MPC cascade control solution is proposed here to bridge the gap between planning and control. Currently, the planning solution is used as a form of open-loop control. With proposed solution, the planning model can be further fleshed out with dynamics and used in the master MPC loop. So in other words, a form of planning optimization can be executed in the master in closed loop and in real time. This new proposed solution also provides better scalability. This solution is suitable for plants small or large. We just need to increase the number of slave MPCs. So finally, we believe we've got a way to break the glass ceiling of upward mobility. This solution also provides a better operability. As we shown in the simulation, we lived through 3 unit shutdowns. That's good enough for our customer. The real-time responsiveness is also very much increased because now master can be run like a regular MPC. So its execution frequency can be scheduled based on the user needs, how fast they want the master to respond to disturbance or to whatever the event. A large class of MPC, just-in-time manufacturing problem can be better solved by this proposed solution. By this time, it should be clear now why planning solution or scheduling solution for that matter cannot be used in closed loop. It's not because those solutions don't have dynamic models. That is the reason, but that can be fixed very quickly. The main reason is that those solutions models the process at the core scale. They don't have any ability to model the constraints inside the unit. In other words, those solutions cannot guarantee its result will always respect the constraints inside process unit. So the fourth one is that we performed a study with the customer. The study results suggest that the current open loop planning solution leaves a lot of value on the table. In this specific example, there's $65 million a year left on the table. And the proposed MPC Cascade solution can capture $22 million a year. That is without change of production rates. If the production is allowed to increase, then the benefits value is going to be even higher. I have the numbers, but I don't have the clearance to share with you. Future work. Certainly, we would like to have a more efficient method to estimate the feasible region defined by the constraints in the slave controller, particularly for the case where the number of conjoined MVs is greater than 4. For most of process units that we have dealt with, the number of conjoined variables typically is 1 to 3 per slave MPC. 4 is fairly rare. 5 is even rarer. Now, can we actually cascade the master MPC one more time outside of master MPC loop? In theory, that's doable to control even bigger scope of supply chain. For instance, multiple refineries include fuel depots and the gas stations even. But we just started looking at this problem. We don't even have a possible applications that we can look at. So this presents maybe a fertile ground for new research, maybe, and possibly more collaboration between industry and academia. With that, I'd like to thank you for your attention, and I'd like to conclude my talk.
Okay, thank you, Joseph, for a very interesting example of algorithm engineering from industry to solve a very complex and highly structured problem. With that, this concludes our plenary session for the evening. I understand the buses are going to be waiting in front of the convention center to transport us to the banquet, and look forward to seeing you all at the banquet tonight.